Right, so good afternoon, everyone, and thank you for the introduction. Today, I'm planning to talk about a recent work in collaboration with Alexey Karapetyan, and it is about homogeneous operators in a sense which is probably more general what many of you have seen so far. So here is the structure of my talk. Well, from this angle, I don't see even my own slides, so let me step down a little bit. The structure is going to be as follows. We have a motivation where I'll begin with the most classical, the simplest situation of homogeneous operators, homogeneous integral operators, and we'll try to see the principles, the simplest ideas behind these situations, and then in the second part, we'll try to develop a more general theory on those ideas and see what happens in that generality. And finally, we'll come to a number of examples which are carried out explicitly, and we'll see some explicit formulae that demonstrate, that exhibit the phenomena that we see on an abstract level in the general part. So let me begin with the motivation. Here is your favorite classical integral operators with homogeneous kernels on the half line. So we have an integral operator with an integral kernel small k, and the condition, the classical condition of homogeneity is that for every x and y and for every positive number lambda, the simultaneous action on both variables x and y by lambda in the kernel throws out a factor of 1 over lambda. Right? This is the condition, the classical condition of homogeneity. Now, remember that the kernel itself is only an auxiliary object. The main object of interest is the operator itself, and the kernel is under an integral. So in fact, the first quantifier can be loosened a little bit, and we can say that this is required only for almost every x and y, rather than for every. So there is, of course, also an analog in Rn, where you add some rotations. So again, you have an integral operator, and the classical condition of homogeneity of such an operator is that for every x and y and for every lambda positive, the simultaneous action on both variables in the kernel throws out a factor of 1 over lambda to the n, right? N being the dimension of the space. And also for every x and y and every rotation omega, the simultaneous action of the rotation on both variables gives nothing. It preserves the kernel, right? So again, remembering that idea regarding the almost everywhere part, we can cast this condition into a more compact form, namely that for almost every x and y, and for every element of the product group, lambda comma omega, the simultaneous action on the kernel gives you a factor of 1 over lambda to the n. Now, let's go back to the one-dimensional situation and try to understand, so what does that homogeneity condition give? Why do we introduce it in the first place? And why especially lambda times x? So the first thing that we notice is that, well, if you have an integral operator, one of the main tools you apply in analyzing it is substitution of variables. And the last thing you want when you substitute a variable is a variable Jacobian, right? So the dilations are good in that they provide you a constant Jacobian, a good thing. So that's one idea behind choosing especially this kind of transformations in the space. The second idea is, why do we choose especially that kind of homogeneity condition for the kernel? Just because it absorbs that Jacobian, right? And as a result, you have the invariance of this, let's call it a density, under those kind of transformations. So that's why you are doing it. And you can write in terms of the kernel that condition as what we call a strong homogeneity for the kernel function. It is that for almost every x and y and for every lambda, this condition holds. 1 over lambda factor pops out. Now, but let's remember again that the kernel is an auxiliary object. What we need from the operator itself is in the integral form, actually. So we want that this integral remains invariant under the variable substitution. for a fixed lambda. That's what we're gonna use in every analytical argument later with homogeneous operator. So in fact, what is necessary for the operators, from the operator's point of view, is the other order of quantifiers in the statement. For a fixed lambda, for almost every x and y, this condition holds. And this is a little bit different than the previous one. It's a weaker condition. We call it weak homogeneity of the kernel. And know that in the previous case, if you think of the set of x and y on which the condition is violated, it must be a null set because it's almost everywhere, right? That null set is the same for all lambda. It's universal null set. Or in the other way around, the set on which the equation holds is universal. It doesn't depend on lambda. Whereas in this weak case, it may depend on lambda. And if you take the intersection over all lambda, you get even an empty set, right? So this weak condition is what actually your integral operator cares about. But it is so weak, it doesn't allow you to say good algebraic things about your kernel. So more practically, you choose the stronger version. Now, with these ideas, let's go to a more general situation and try to develop a corresponding generalization. So what we take is a measurable space. We fix a measurable space M from a certain category. Say, it may be an abstract measurable space, or it may be a topological space with its Borel measurable structure, or it may be a manifold with its smooth measurable structure. So once you fix a category in which you embed the object M, it also fixes the admissible transformations, its automorphisms in the category, right? So they are going to be either abstract measure space automorphisms, or homeomorphisms, or diffeomorphisms. And all the rest of the constructions in this talk are going to be the appropriate structures to the category that you have fixed from the very beginning. So we won't worry about those things anymore. And the definition is this. So you have a measure space M, so you choose a measure on that measurable space, and you say an appropriate transformation phi is a dilation if the pullback of the measure mu under that transformation is proportional to itself with a certain positive proportionality constant lambda phi. Yeah, and that's it. It's just two different ways of writing the same thing, right? It's proportional to itself after the transformation. Now, we put forth the following setting for the problem. I have a measure space. I choose a group G of dilations as defined in the previous slide on the measure space. And then in order to facilitate that group theoretical language, instead of writing transformation phi that maps x to phi of x, we write the transformation G, an element from the capital G that acts from the left on the point x. So you have a left action of the group on the space M. Then we assume that this action is transitive on M for the simple reason that whatever we're going to say now is going to pertain to every single G orbit separately. So it only makes sense to consider only one orbit at a time. So we take the G action transitive. Now this correspondence between the dilation G and the corresponding proportionality constant lambda G turns out to be a group character, a group homomorphism from G to positive numbers, and we denote this character by lambda, and we assume it's fixed. Now, all those transformations G, which are in the kernel of this character, they actually don't change the measure, right? And if there is an appropriate notion of a dimension in the group G, then you'll see that the kernel of lambda is a co-dimension normal subgroup in G. So the vast majority of these transformations don't actually change the measure. But unlike the classical case where we were able to unambiguously factorize the group into SON that doesn't change the measure and R that does change the measure, in general, we won't be able to factorize G into such two groups, the kernel and something else. So we'll refer to all elements G as dilations, no matter whether actually they dilate the measure or not. Okay. So you remember the weak and strong homogeneity in the case of the half-line. We give the corresponding generalizations in this setting. So we have a measurable kernel function and we call it weakly homogeneous if for every dilation G for almost every x and y, this condition, pretty much reminiscent of we had originally, holds, and we call it strongly homogeneous if the same holds but with the two logical quantifiers swapped, right? So for almost every x and y, a fixed set, for every G, the condition holds. Let me see the time. Okay. So now the transitivity, the assumed transitivity of the action of G on M allows us to identify M with the homogeneous space, the coset space G by H with a certain stabilizer subgroup H. And here we are at a junction. All what we're gonna say from now on is gonna be different between two cases. Case A, where the stabilizer subgroup is in the kernel of the character, which means that the restriction of the character on the stabilizer subgroup is trivial. And second, not the case, right? And we'll see that these two are qualitatively different situations. Namely, in case A, you will be able to reduce the problem of your homogeneous operators to problems of invariant operators in a space with an invariant measure. So your beautiful harmonic analysis and convolution theory. In case B, you won't be able to reduce it. All you have is going to be what you have. Right, so what can be done in case A, namely, if you allow me to denote by G to G capital H, the canonical quotient map, then the vanishing, or not vanishing, the triviality of lambda on the subgroup H allows you to project it down to a well-defined function lambda tilde on the coset space, and then you use that lambda tilde to define a new measure mu tilde, which is now an invariant measure, right? You take the original measure, which was dilating, then you produce another measure, which is invariant, and it's related in this simple way. You specify the Radon-Nikodym derivative, simply. So then what you do is for every positive real P, you construct an unitary operator UP from LP space with the measure mu to the LP space with a measure mu tilde. And it acts in a simple way. It just acts by multiplying by a certain power of lambda tilde, right? And then this will allow us to translate problems from the original measure space to the new measure space being invariant, your classical harmonic analysis. So the so-called quasi-regular representation of G on the coset space is simply acting by pullback of the dilations on functions. So because the measure mu tilde is invariant, these operators LG turn out to be unitary on every LP with the measure mu tilde. Moreover, the last line, there is the simple intertwining property between the UP and LG, and this allows you to relate the LG's action in the original mu measure space with its action in the new mu tilde measure space. Let's talk a little bit about the geometry of dilations, namely some special sets in regards to the G's action, the dilations action on your space. Now, we introduce this curly X set that depends on the stabilizer H and character lambda. This is the set of those points in your space where there is an element of the stabilizer subgroup H which doesn't move the point and yet changes the character. So this is a pathological behavior, and we'll see that because of that, your homogeneous kernels are going to be singular at those points. So in case A, we'll see, or we can see, that the curly X set is empty. So you can have regular homogeneous kernels, as is the case with convolution kernels, right? Because as we said, everything is reduced to convolutions, if you wish. In case B, the set is not empty, so you have only singular homogeneous kernels. So further, if you allow me to introduce some notations, I denote by m star the rest of your space. So everything but this bad set curly x. And if I denote by ph the canonical quotient from the coset space to the double coset space, then the h backslash m star is simply the image of the good, the regular part of your space under this quotient map. So let me elaborate a little bit more on geometry. What you can construct then is a geometrical line bundle over the space h backslash m star, and you can come up with an embedding of the space of all measurable sections in that bundle into the space of all measurable spaces on the good part of your space. And we'll see why it is important pretty soon. But before that, let me also introduce the following class of functions on your space, the curly f. These are all functions which behave in a certain way with respect to the left action on the argument by elements of the stability group. And you can see that it is kind of similar to the homogeneity condition for the kernels, aside from the fact that this is for a single variable function, right? So it's harder to satisfy. So all functions, or measurable functions that satisfy this, are collected in the set curly f. And the important thing is that, well, it turns out that curly f consists exactly of those functions which vanish on the bad set, and on the good part, they are nothing else but in the image of the embedding p on the first line of sections in the bundle tau. This gives a bijective correspondence between arbitrary sections in the bundle and functions f that satisfy this condition on the second line, right? Okay, now let's come to the homogeneous operators themselves. So I have a vector subspace of all measurable functions, and I have a linear operator k. We call the operator k homogeneous if the domain is invariant under the transformations from G, and the operator commutes with this quasi-regular representation. So basically, your operator is invariant under dilations. We call such operators homogeneous at this level. So in case A, what you can do, use your unitary operators UP. You first transform the domain, and you show that if the original domain was invariant, then so is the transformed domain. Then you form the unitarily transformed operator k tilde p, which acts now in the new domain. And you show that because of the intertwining property between UP and LG that I showed you before, the newly constructed k tilde also commutes with LG. But now this happens in the space of the invariant measure nu tilde. So you have now not a homogeneous operator, but a G invariant operator in a homogeneous space with invariant measures. So you're back in your old and beautiful harmonic analysis and convolution theory, right? What about the integral operators? So let me have time first. Okay, thank you. So then you have a kernel k, which is simply a measurable function, and you have an integral operator k. It is called an integral operator if its action on a function from its domain is almost everywhere given by this integral formula. You interpret this integral the way you want. If it converges in the usual Lebesgue sense, then fine. If not, then you have to come up with certain conditional convergence scheme. Now, and then homogeneous integral operator is just an integral operator which is homogeneous with the definition we gave on the previous slide. Now, the first result is this. So in order to obtain any reasonable results, we need to assume that the domain D is not too small. So in particular, we assume that it separates points in the following sense. It contains a sequence of elements, the domain D, such that if a certain integral vanishes on the sequence, then it vanishes identically. a pretty natural kind of condition, which you can easily show is satisfied in all reasonable situations. Now assume that that's true about the domain D, and the domain D is invariant under dilations. Then an integral operator is homogeneous if and only if its integral kernel is weakly homogeneous, as expected, right? So the homogeneity of the integral operator is equivalent to the weak homogeneity. However, as we said, we won't be able to find beautiful formulae and solutions with weak homogeneity, because weak homogeneity simply says for every translation there is a subset, but these subsets may be different for different translations. And actually, we managed to produce a counterexample, a horrible one, which is weakly homogeneous yet not strongly homogeneous, as far from strongly homogeneous as possible, right? On the other hand, if we take, for practical purposes, the stronger condition of homogeneity, then we can show that this is equivalent to the kernel having the following form. This is a little bit reminiscent of the convolution case, but now it has this 1 over lambda a factor. If you don't put that factor, then this equation won't make sense, right? So it's a little bit different. And the function f is not an arbitrary function. It must be from the curly f space, right? So what does this give us? It says strongly homogeneous kernels are in bijective correspondence with functions from curly f, but functions from curly f were in bijective correspondence with sections in that bundle tau. So you have a parametrization, if you wish, of all strongly continuous kernels in terms of sections in a given geometrically constructed bundle. So this also shows, because as we said, the functions f are expected to be singular on this bad set curly x, that kernels given by that functions will also be singular exactly on that set. Now let me go to examples, and there will be a few of them. The simplest example in this respect is the cylinder R times T. So in this case, the space and the group are the same. The stabilizer subgroup is trivial. Group elements will be denoted by a comma phi, a on the line, phi on the circle. And the coordinates in the space are again zx on the line, theta x an angle. The action is the usual multiplication on the cylinder. I take the measure to be e to the 2zx times the Lebesgue measure, and this is exactly the measure that dilates with the character lambda equals e to the 2a. Now, in this language, the strong homogeneity condition is written over there. I won't read it off, it's a little bit too long. More importantly, the general form, according to our theorem, the general form of the strongly homogeneous kernel is given over here, where f is an arbitrary function of two variables, right? So, well, this is probably not new. Now, what is new is that because it's a case A situation, you have two ways of obtaining this. First is reducing everything to convolutions. This result can be obtained by convolutions, purely. And second, simply following our construction, going to see what the bundle is, in this case constructing, seeing that the bundle is trivial, and therefore you have arbitrary functions f without any topological identifications, and constructing the solution all the way to the final formula. So two ways. Now, the next example is the plane R2. This is just a very simple situation. So here you take M to be R2 minus the 0 point, because we agreed that the action of the group G is transitive and the 0 point is a fixed point. We remove it. It doesn't change much in your integrals, of course. The group is still a cylinder that acts, and the group elements are in the cylindrical coordinates, whereas the elements of the space are in polar coordinates. And the action is given in a radial form, so there is a standard rotation and a certain dilation which acts radially. the measure is their usual Lebesgue measure, and well, the character is e to the 2a. In case of this group, there aren't many characters to choose from. It's always something of this form. So the strong homogeneity condition is written over there. It's nothing new there. Now the general form of the strongly homogeneous kernel is this, right? And this is again something familiar. Well, in fact, there is also a note that is due here. Sometimes in the literature, you can see a statement that the homogeneous kernels are functions of the absolute values of the points and their scalar product. You can see that that's not quite true, because this is an arbitrary function of the second variable, not necessarily an even function. So the statement would be true if you consider not only rotations but also reflections, in which case you would rule out the odd functions from there. So this is the general formula, and now you can do it in 3 ways. You can achieve this result in 3 ways. One way is, well, reducing to the cylinder by transformation. The second way is just looking at it as a case A situation and reducing to convolutions directly. And third, following our way, right? 3 ways to obtain this same formula. Now, a particular case which Alexei also discussed in more details yesterday, I won't stop on this transformation, is the relatively newly introduced Adama-Bergman convolution operators, which you can write as a homogeneous integral operator. Right, and in that case, the unknown function f is this one, which is related to the kernel G. Right, now let's consider a little bit more general situation. You have a disk on the plane with any radial measure, right? So your measure is, as written on the second line, it's a certain, almost everywhere positive integrable function gamma of Rx squared times Lebesgue. You have the character lambda, which is e to the 2a. You have the cylinder that acts by rotations and by certain unknown, yet unknown radial transformations. And you want to find those radial transformations, the new dilations, so to speak, which make your radial measure pop out a constant Jacobian e to the 2a. So if you write down that condition, that the Jacobian is e to the 2a, you get an ODE which you can solve. But there is an easier way of solving this problem, namely, you can try to find a transformation of this disk into the full plane in a way that it flattens the gamma into a constant. So it transforms your measure space into the standard plane. For the standard plane, you already have the formula in the previous slide. You transform it back, and you get this formula. Namely, if for gamma you denote by capital gamma this indefinite integral, for every choice of the parameter c for which this capital gamma is everywhere positive, you get a different family of dilations that satisfies the same condition of popping out that factor into the 2a. And for every such choice of dilations, you get the corresponding general form of the homogeneous kernel. It depends on c, of course. So this is simply an application of the same theory. Again, you can do it in both ways because it's a case A situation, right? In particular, you can take the Poincaré disk with half measure. And in this case, your gamma t is 1 over t squared. You compute this antiderivative. And then plug in, you get the following explicit formula when, well, you pass to complex coordinates because they are more natural for the disk on the complex plane. And this is a formula for the most general strongly homogeneous kernel on Poincaré disk with respect to those dilations which behave well with the harm measure on the disk, right? So G is an arbitrary function of one real variable and one complex variable on the unit circle. Another case of this category is the so-called, again, relatively newly introduced weighted Bergman measures. So you have a parameter alpha from -1 to +infinity, and you have a measure of this form, which is a certain constant times 1 minus r squared to the alpha times Lebesgue, right, on the unit disk. And then again, you have the gamma explicitly, you compute the capital gamma explicitly, you plug in the formulae, you get this beautiful formula for the general homogeneous kernel with respect to those dilations which transform this radial measure to something proportional to itself, right? Again, every choice of the parameter c results in a different family of such dilations. And correspondingly, you have the general formula for the kernel. Now, let me give you an example which probably you haven't thought about. And this is a case B situation where you can't rely on convolutions. Namely, let's take Rn and let's consider as the group of dilations the full general linear group. Okay, so my M is Rn with the origin removed, the punctured plane, and my G is the full general linear group. The stabilizer subgroup is the affine group in n-1, which is basically that semi-direct product written over there. You have Lebesgue measure, and your character is nothing else but the absolute value of the determinant of the matrix, right? Now, obviously, looking at H and looking at lambda, you see that it's not true that lambda vanishes or is trivial on H. So you are properly in case B. You know you won't be able to use convolutions. You know you expect singular kernels. So for n greater than 2, you compute this curly X set, the bad set. You see that it is the whole space. The whole space is bad, right? So only trivial kernels, k equals 0. There are no solutions. For n equals 2, interestingly, the curly X set is, well, the horizontal axis without the origin, because the origin is removed. And when you compute that set H backslash M star, it turns out it's a single point. Now remember that we made a bijective correspondence between all strongly homogeneous kernels on one hand and all sections on a bundle over this space on the other hand. If the base of the bundle is 1 point, then the space of sections is a one-dimensional vector space. This shows you that the space of all homogeneous kernels is a one-dimensional space. You have up to a constant a unique homogeneous kernel in this case. And that is this kernel, kxy equals 1 over absolute value of the scalar scalar cross product of two-dimensional vectors x1, y2 minus x2, y1. And the corresponding integral operator is this. You see, because the kernel is, well, as expected, it is singular, but it's also everywhere positive. In order that this integral converges in some reasonable sense, you need to pick functions f inside which are very anti-symmetric in many different ways, so that to cancel the positive and negative parts of the integral in some principal value sense. So this makes the domain of such an operator very narrow. It's not very useful. So what you want to do, you want to find an integral kernel which is anti-symmetric itself, so that at least for some continuous functions f that are continuous on the bad set, you can give sense to the integral from principal value perspective, that the integrals positive and negative parts cancel each other. So you want some anti-symmetry in a sense. So what you do is, now you say, well, let's consider only orientation preserving matrices, right? Only matrices of determinant, positive determinant. So you take the GL plus n, the corresponding stability subgroup is over there, again, affine plus. In n greater than 2, still the bad set occupies all of your space. Nothing. There are no non-trivial kernels, homogeneous kernels. However, in n equals 2, the H \m star becomes a 2-point set. So now your space of homogeneous kernels is two-dimensional, and that's exactly what's written over there with two constants c plus and c minus, depending on the orientation of the two vectors x and y. If you want to make the operator anti-symmetric so that its integral in the operator can be made sense of for continuous functions, you need to choose c plus and c minus the same. And as a result, you have a unique up to a factor anti-symmetric homogeneous kernel, which is over there 1 over this cross product. And there you have this integral operator, which is a very interesting and strange one. And note that if very formally you restrict x2 to 1, and then in the integral you restrict y2, you accumulate the integral over y2 equals 1 in a sense, very formally, then you recover Hilbert transform. So this is kind of a two-dimensional modification of a Hilbert transform, but unlike the Hilbert transform itself, which you just write, I don't know, does anyone know a good justification for the introduction of the Hilbert transform? People just write it and see that it's wonderful, right? In this case, this operator arises naturally as the unique anti-symmetric homogeneous operator, which is invariant under all orientation-preserving linear transformations. So we are still thinking how to make sense of this operator together with Alexei, and hopefully this will appear in another publication. So I'm close to my conclusion, and what we have done is we introduced dilations in a measure space, and we studied the geometry of dilations. And then we distinguish between two cases. Case A, where you can reduce everything to G invariance in convolution theory, and case B, where there is no such reduction and you expect only singular kernels. Then we saw that homogeneous integral operators are exactly those integral operators with a weakly homogeneous kernel. And also we show that if you instead impose the strong homogeneity condition on the kernel, then there is a general formula which can always be explicitly computed if everything else is given explicitly. And we considered some examples, cylinder plane, including the Adama-Bergman, the radial case, they are all case A, and we came up with a strange, unique, singular operator for the case B. So what remains to do? First, it remains to understand the structure of singularities and how to regularize the corresponding singular operators in case B, because your kernels are always going to be singular. This is something we are also working on. Then, to understand that unique operator which we have already found, this the one related to the Hilbert transform, in fact, you can show that it can be factorized into the action of a Hilbert transform and the Radon transform and something in between, but maybe it has some further realizations as well. It's an interesting case which needs to be studied separately. Another open problem is, well, what to do if n is greater than 2, right? So we saw that the full general linear group, even those orientation preserving, are too many to allow any room for a non-trivial kernel. So we are looking for a reasonable restriction of the group G from the general linear group so that to find again a unique natural homogeneous operator for higher dimensions as well. And finally, well, this is all about the structure of the operator and so on, but we are also looking to do operator theory, namely how such operators act on function spaces. There is a great deal of information about this for the classical situation. So we are looking to see what the natural function spaces are and how these integral operators act on those function spaces and what properties they possess. So this is all I wanted to tell you. Here you can see the paper's preprint. And yeah, thank you everyone for your attention.
some words. So Zhirayr presented very nice general theory, but the real study was the opposite direction. Because we started with examples, and it was like 3 years ago when we met each other in Santa Barbara. And the idea was just to take a homogeneous operator in classical sense on a plane and try to reduce it to the disk. Because at that time I've been thinking about kind of the resin transform something with Professor Kevin. So kind of invariance was involved. And when we did this, we reduced this integral operator plane to the unit disk. We came up with kind of ugly kernel. I mean, it's very specific kernel. What the heck is on the function doing? But it appears that after thinking, that there must be a reason for this kernel to be such. I mean, and the reason was presented here very beautifully in general theory. So the thoughts came to this classification. And also, I guess it's important that Zhirayr told that inside of this study, there are some very particular interesting operators, like the last one operator, that actually Zhirayr told you that it connects also radon transform and Fourier transform. It is not in the article, but if you apply Fourier transform separator, you recover radon transform. This kind of connection is very nice, I think, for those who do that job. In geometry.
More comments or questions?
So
You said that N can be an abstract general measurable space. Have you thought of maybe considering an effect algebra such a?
To be honest, no. And to be very honest, I heard of effect algebras yesterday. So,
Generalization of Boolean algebra. Usually, when you think of measurable spaces, that's just a statement with a sigma algebra or just
right.
a Boolean algebra of sets.
Right.
And effect algebras are just a general, natural generalization of Boolean algebras, and you can define measures or also effect algebras.
Right, that's something I need to look up, certainly. Thank you.
And for the subgroups of the general linear groups, suitable subgroups, have you considered subgroups like, I don't know, linear isometries or things like that? Or orthogonal matrices?
Well, we didn't do any of that so far. This work is pretty recent. We submitted it in a month or so ago. Thank you.
Yes. You see, the title of your talk is Homogeneous Operators, Integral Homogeneous Operators.
Right.
So it is reasonable to expect that you will provide several examples of the applying of your very general approach to some homogeneous operators that are not integral ones.
Well, to that question, I only have a partial pseudo answer. Namely, in case A, because everything is reduced to the harmonic analysis on homogeneous space, I can take just an invariant non-integral operator, which can be constructed from a spectral theoretical perspective, just out of harmonic analysis, in the invariant measure set and translate it back to this situation. That would be an example. But that's kind of not fair, because, of course, the whole meaning of introducing new machinery is for the case B, which there is nothing else to do with. And exactly, and I have no examples, unfortunately.
More questions?
Yes. You mean that basically this integral operator singly to write down, not this that before?
We haven't seen it studied so far. But again, this is something we did pretty recently. So if you know everything about this, we are absolutely glad to hear about it.
It's very similar to Hilbert transform. It's
Looks like, but
it is different than what usually studied in combinatorial. So because there they have singularity at the point. Here it's spread out.
Right.
So maybe that's
That's why you can write it as, because it's a double integral, you can write it as an application of a certain pretty regular integration operator and a one-dimensional singular that exactly does the job, right? So you have one-dimensional singular and one-dimensional. Yeah, that's what happens. You write it as a Radon transform and Hilbert transform combined, or Fourier transform and Radon transform combined. So, but where is it applied and what properties it has?
You see, this product is very, very strange because in the sense that it takes every function, it makes homogeneous function because the image is homogeneous function only.
Order -1, right?
Yes, order -1. Right. For every f, you have homogeneous function. So cut some.
projective.
Yeah.
No questions?
So if the function you start with this homogeneous already,
No, f
no, I understand. Suppose that it's homogeneous already. What that means? Is there a simplification equation?
No idea so far. So we are still trying to understand it.
More questions? I have a very special question on the example 3.
Example 3. Let's go back.
First,
Here?
First.
Yeah.
Yes. What does it mean 2 pi? We have the second element modulo
Yeah.
2 pi.
Right.
Why plus 2 pi?
Because it's a difference, it may go negative, whereas in my convention I take it from 0 to 2 pi. So,
For positive.
yeah.
Thank you. More questions? Let's thank